So, an ingenious method for removing the car, blah blah. Okay, I get it. So, well, let's draw it like this. So let this be the mud puddle. I'm not talking. Uh, Basta acqua! Basta acqua! Okay.
Hello?
Okay, yes, I'm back. I'll be
Okay,
back.
yeah, that
Okay.
hello. Okay, yeah, you suddenly went quiet.
Doesn't matter. So,
Okay.
so I drew the problem. The driver pushes in the middle like this.
Yeah.
Would you like to put down the information that the mud holds the car in place with a maximum frictional force of 5,000? Talk me into this a moment about the friction and something else, please. Joy feedback diagram.
Okay, wait, I was confused. Okay, well, this is the side view. So, wait. Yeah, no, wait. No. It's 5,000 newtons. Wait, no. Friction will be going opposite of whichever way.
I drew it. I don't know where you are, but I drew it up there.
Oh.
Yeah, I already did. Okay, let me come to you.
Wait, where are you?
I was back up.
Oh, wow.
Okay, let me draw it one more time. Allora.
Sure.
So let's draw the mud paddle here. Mud. The tree. And the car. Like this.
Yeah.
Okay.
Well, okay, wait. When we worked on it in class, we drew it more like.
Okay. Well, it's what's gonna happen. It's what's gonna happen. Anna, are you coming back on camera, or shall I save some battery and shut off mine as well?
Wait, can you also shut off yours because my Wi-Fi has been worse lately.
Okay,
Like,
no
I
worries.
think
Yeah,
that's
yeah,
why
sure.
it's
Okay,
not.
okay. That's it. Thank you for saying that. Okay. Okay. So what happens? You push here, and what happens?
Well, when you push it, there's force applied. Like, the friction is gonna be in the opposite direction from where it's being pulled.
Mm-hmm.
So, and it's essentially being pulled this way. So this is Ft, and then this is F friction. And then we also have this, which is equal to 2 degrees. Okay.
Okay. Hold on a second. Can't die. No, nothing. I'm back. Just hold on a second, please. Just one moment. Okay, I'm back. I'm back. I'm back.
Okay.
So, what are the steps that we are going to put down? Why is this a really, smart trick?
What?
Why is pushing it this way a really smart trick?
Something, the tension gets distributed and magnified, blah, blah, blah.
So let's draw the free body diagram. You put tangent. Where is the tree and where is the car? You should label them, otherwise it is hard to understand. This is car. Let this be the tree. So you push here. Go on with you drew only one tangent, and this is bad because we have the other tangent this way.
Yeah, that way.
This way and this way and that way, isn't it?
Yeah.
Okay.
Okay, wait. And I know the fact that there's angles means that there is like a horizontal and like a vertical.
Yes, it is.
But
It is.
I don't know how to like incorporate it.
Well, we are gonna have T up and T straight, isn't it? Something like this.
Yeah.
So, like this. The horizontal force on the car and on the tree is going to be the same. The only point is that the tree is not going to move while the car is. So if we say that this is theta, the horizontal force is easily 2 cos t cos theta, and the vertical one is t sine theta, isn't it?
Yeah.
Okay.
We're
But
going with the general right now.
yes, at the push force here, since you have twice the vertical component to be taken into account, you have that F push is equal to 2 tangent sine theta. Since you are only pushing vertically, right? You are only pushing vertically.
Yeah.
Like this.
Yeah.
Then, to start moving the car, we need a t cos theta be equal to 5,000, isn't it?
Yeah.
Now we can happily extract t from this one and write that t is 5,000 divided by cos theta. And we plug it in the second one.
Yeah. Okay.
So that f push is equal to 2 times 5,000 over cosine theta times sine theta. And this is as happy as 10k tangents theta, isn't it?
10k tan theta.
Tangent theta, yes.
Tension or tangent?
Tangent, because we have sine divided by cosine.
Okay. Just double checking.
Yes, please.
Sounds okay.
Now, as a more general approach, for small angles, we can simplify that the tangents of the angle is more or less like the sine of the angle. And we are gonna need this type of simplifications later on when doing optics. Eccolo qua. So for this point here, we can happily write that tangents theta is more or less equal as d divided by L, where if the distance car tree, let it be, I don't know, 10 meters,
yeah,
and you push half a meter, then you have that the tangents of theta is more or less equal to 0.5 divided by 5, because we use half the distance, right?
yeah.
And so we only have, in this case, it was 10,000. In our case, it's gonna be down to 1,000 Newton.
Wait, okay. So basically the force of pushing is 1,000 newtons.
Yes. Even if, and this is, I want to put it down red, even if static friction is 5,000, a 1,000 Newton is enough.
Okay.
That's it.
Yeah. Okay.
Please notice that this is an approximation.
And data equals to distance divided by length.
Yes, exactly. New problem.
41.
Same chapter. So let's go down. I don't know. Let's go down. Oh, this was problem 38, right? So let's write it big like this. Like 38, chapter 3. And we are gonna hear. Can you hear my children screaming from the bathtub?
Very cute. Yeah.
Okay. 41/3. Okay. So a 1.5 chunk of slide. Oh, ice slides down a roof. Would you like to draw something in the meantime, please?
Like draw the free body diagram?
Well, draw the sketch first and then the acceleration of the ice. Well, it's not gonna be like that. Come on.
No.
Come on,
I
princess.
know.
It's gonna be at least. It's gonna at least be
But
like
how do you
this.
rotate it? I can't rotate it. Anything here.
Just click on it. You have the blue dot. You click on the blue dot and then you move it left and right.
Where's the blue dot?
On the top. Oh, I clicked it. Just draw something else. You just draw like this. You select it and you have the blue dot.
Okay, and it's 1.5 kg.
Yes. With a 60 degrees angle like this. So A, ideal world, no friction. What is the acceleration? That's easy.
-9. No, because it's not.
Okay, let's quickly remake a small recap on this one. So the only thing that acts is weight. So we write here P equals mg, right? But this is inconvenient because our reference axis is rotated, so it's tilted. Then we decompose, and I still remember how you hurt me with my decompose or decompose weight along the perpendicular axis, which we will call y, and the parallel axis, which we will call x. So here we have P perpendicular equal to mg cosine 60. And here we're going to have P parallel, which is going to be mg sine 60. Then we realize that the block does not move within the surface, and we conclude that we have this one, so the normal reaction of the surface.
Yeah.
And in this case of the ideal world, that's it.
Wait, and so then the normal force is mass times gravity cosine 60.
Right. Mass times gravity cosine 60. Which happily cancels this out like this. Hold on a second, I want to schermo e luminosità, devo anche mettere un pochettino più bassa, blocco automatico mai. Okay. Otherwise my stupid screen is always getting dimmed and I don't like it. So what is the acceleration in the ideal case?
The acceleration is mg cosine 60.
Okay, numbers.
Oh, you
Yes, because the answer was wrong. I want you to calculate. Oh my god. Oh my god. Do you mind if I mock you sometimes a little bit? Just a little bit.
Yeah.
Oh, you do? Okay, I won't.
But I
Okay.
don't mind.
Ah,
Like
you
if I
don't
want.
mind. Okay, you don't mind.
Wait, if you what?
I mock you a little bit.
Oh yeah, I don't mind.
Okay, that's good. Sense of humor is the greatest thing a man can appreciate in a woman, by the way. Yeah, really. So what is the acceleration? Your first answer was mg.
No, wait, it's sine 60.
Yes, your first answer was damn. What is the back here? Sine 60, and I tell you, no way. Catastrophe. Catastrophe. Why is that a catastrophe? You know, I kicked out of the course, of the physics course, more than one student because of saying this. Hello. Hello. Hello.
Hello?
Oh yeah, okay, I'm here.
Okay, wait, now I can hear you. Yeah, the Wi-Fi is bad today. There's a lot of construction, so maybe that's why.
So why did I kick out a lot of students calling me that the acceleration was mg cosine or sine, doesn't matter?
Wait, I didn't hear the first part of your question.
You told me that I am still writing on the board anyway. So you told me that the acceleration was mg sine or cosine, it doesn't really matter, 60. And I told you that this is a catastrophical answer, and I kicked out of the course, not of the exam, but of the course, several students claiming similar facts.
That it was sine?
No, it doesn't matter. We can happily do like this. Look, we can happily write mg f theta. Doesn't really matter what f theta is.
Oh. Wait. And you're like asking why is this wrong?
Yes, why it is catastrophically wrong. You said that A is a matter of m, g, and the angle.
Well then, I don't know, because acceleration is mass, it's like relative to like your mass to your net force.
Mm-hmm. Right. So you are even telling me now that acceleration depends on mass.
Yes.
Okay.
Does it not?
Well, you should tell me whether it does or not.
It does.
Galileo Galilei proved that out of the Pisan tower, he threw an elephant and a, like a small glass ball, and they both landed at the same time. It was pretty difficult to carry an elephant up the Pisan tower, but still he did it for the love of physics. This is supposed to be a joke. You can laugh or at least smile. Okay.
I laughed.
Okay. So in absence
In
of
absence.
friction, acceleration does not depend on mass. because A is equal to the gravitational acceleration of 9.8066 meters per square second.
Oh, yeah. So the acceleration is always 9.8?
Yes, on Earth. That's why I wrote that A, what is it here? A is a function of the mass, the gravity, and the angle. And then I tell you that the mass is excluded. But if we went on Mars or on the moon,
I'm confused then. How is mass? Like, okay, wait, I understand that absence of friction.
no, just have a look at this one. How much is the force? The weight force is mg, right?
Yeah.
In basca? Dove si è? Cioè devi essere là, mi l'ho messo là l'ultima volta. Domandi. Aurelio? Ah, giusto, te ragione. Hold on a second, please. One more moment. One of the kids it may be missing, but I don't think so.
Oh.
Ah, damn. No, everything is fine. He's just quiet, which is strange given that both are Italians. Okay, so the force is mg, and the acceleration is force divided by mass. So we have mg divided by m, which happily simplify.
Mg divided by m.
Yes.
It's g. Hello?
Yes, I'm here.
Yeah, mg divided by
M.
just g.
Yes, exactly.
Yeah.
And both are, this is the second Newton's law. Second Newton's law.
Yeah.
Okay. So acceleration does never depend on mass. Why did I say in absence of friction? Let's get a small, deeper level understanding. When friction, air friction is considered, but not only air, because when friction is considered, you have friction equals mu times the normal reaction of the surface, which is gonna be mu times actually no, only air. You see, I am not lecturing, I am reasoning, and that's why if we have mu n equals mu mg cosine 60 in this case, but then the force is depending on the mass, but then to find acceleration we divide the force by the mass, and we have that the acceleration in that case is just g sine something minus mu g cosine of the angle, right?
Yeah.
Okay, now let's get down to air. So air friction acts on the cross section the speed, the viscosity, and basically that's it. Well, and the mass, of course, and the inertial moment. There is a momentum exchange. Momentum is mv, exchange between the body, the moving body, and the medium. The heavier the body moving, the lesser the medium has influence on it. The heavier the body, the lesser the medium interaction. And that's why when you have a slide like this, a toy slide, and you have two toy cars, one is big and heavy, and the other one is like a small motorbike like this, and you let them go both at the same time, what happens in your opinion?
The heavier one goes first.
Yes. Because this one is getting more stopped by air friction. As easy as that.
Yeah.
Oh, by the way, these insights are more logical rather than physical, because air friction is such a pain in the back that actually nobody studies it, and it is mostly approximated.
Really?
Yeah, it is.
Like, not even like the drag, it's
Drag force is something, but whenever you have to study the movement as a function of not only the acceleration but the velocity as well, and the acceleration depends on the velocity as well, you have double derivatives. How is it called? Equation at the derivative, partial derivatives if it is 2D, and usually it is empirically determined. So you get a constant and you multiply by the velocity and forget about it. Approximated. What happens when the speed of the object grows? Viscosity starts changing. Viscosity changes. And so you have something like minus the viscosity times the velocity, but minus the viscosity, which is a function of the velocity, times the velocity itself. And this product makes it complicated to evaluate. Complicated.
yeah, this is complicated.
Exactly. So usually we assume the viscosity independent on the velocity, and we assume it constant. But that is an approximation. So why making approximation that lead to wrong to wrong results, when you can simply approximate it at the very beginning without introducing too many degrees of error? That's my my own idea.
Okay. That's a side quest.
Yes, still I hope I made it interesting and informative. Let's get back to our happy part B here. Part B is how much. Mass doesn't matter, where we have just done it. And then kinetic friction. Mu k equals 0.20. Shall I go on lecturing, or are you up for?
Honestly, yeah. I feel like today is a lecture day.
Okay, so today you are giving it up a little bit. Okay, no worries. Well, so how did, let me make it a little bit more, round then. So how did people understand or actually conclude about the existence of friction? So you have mg, we decompose it like this, like that. We observe, we do not conclude, we observe that this thing does not enter the surface, so we conclude that there is a normal force going up. And then we measure how much time it takes for it to slide down. Time. And the time is greater than calculated.
Yeah.
What is our conclusion? So if the time is greater than what we calculated, we infer that the acceleration is less, and we conclude the existence, there is another force slowing it down. As easy as that. Shall we calculate it, or shall we let it be like this?
I mean,
you can just tell me, no, Philo, let's go for another problem. It's okay.
Let's go for another problem.
Okay, call it, please.
Ooh, I don't know which one. Let me double check. My dorm is disgusting. We just found a centipede in one of our bathrooms. It was disgusting. I just heard them freaking out. Did you hear that?
No.
There was like 3
I live in the forest. I deal with mice, centipedes, dragons, werewolves, vampires, children.
But are they supposed to be in your house?
Oh yeah, not in your dorm. Yes, indeed. Okay, right. I am the superhero here. Right, you are the princess to be saved.
Okay, wait. So chapter 3. I don't know. Oh.
55.
50?
55. I'm just randomly.
It doesn't go up to 50.
Okay, then let's make 45.
Let's do that.
45. Let me have a read. Let me go over, I don't know, over here. Give me a head up. When are the next tests and so on?
I don't know. I think it's finals at this point.
Okay, so what about starting to have a look at math sooner or later?
Math?
Yes, not today, but starting with Wednesday, I would, or is it Tuesday? I never remember. No, it's Wednesday. Yes, it's Wednesday. What about starting to have a look at math?
Okay, actually, yeah.
Okay.
And I can help choose you.
Okay. So the diagram at the right shows two masses connected by the string over a pulley. Whoa. So that's 2. That's 1. This is 30. Well, let's assume that this is 30. It's not specified as far as I am having a look at, isn't it?
Hello?
Yes, I don't see any angle, so let's just suppose 30 theta 30 is the same. Is it?
It's not saying.
No. Let's put it theta and keep it as a variable.
Yeah. Okay.
So let's write a free body diagram for each of the two masses. Come on. By the way, I would like, give me another 50 seconds, stop, and I'll be right back.
Okay, that sounds good.
Okay, I'm back. Sorry, everything's fine. At least, seems like. Yeah. So let's draw a free body diagram of this thing. Don't you want to use this one?
Oh. Wait, I was.
Okay. Yes. Correct. Correct. Now, write a net force equation for M1 and M2.
Okay, like. Okay, wait, so the forces acting on it are. And wait, does the problem say to ignore the force of friction?
The problem says the ramp is frictionless.
Okay. Okay, wait, so it's frictionless? That's good. Okay, so. Wait, I'm just writing down the forces right now. This
Okay.
isn't the force of gravity, but then it would be.
Actually, to be honest,
Would it be force of tension minus the force of gravity?
Depends where you put the plus or minus, but you forgot the normal force here. Otherwise, you must keep into consideration both the vertical and, the parallel and the perpendicular.
Oh yeah, right, that's true.
What is plus? Is the axis pointing like this or is the axis pointing like that? Depending on
Like
this,
plus.
okay, you choose whether to put a plus or a minus here.
Okay, wait, so then that would make it positive then.
Mm-hmm.
Yeah. Okay, wait, and then so then that would be plus. Wait, and then the force of gravity would be negative, right?
Well, yes.
Wait, is it in equilibrium? It's not moving.
Let's say that it is at equilibrium. Otherwise, it would be specified.
Okay,
Actually, stop. We can determine whether it is an equilibrium or not. We can determine that.
well, if there's acceleration or not.
Doesn't matter. Yes, we can find that. But you gotta first write the two net force equation for M1 and M2.
Okay, wait. So force of gravity. Okay, and then plus force of tension. But then the force of gravity is moving the other way, I guess.
Because it is going down like this.
Yeah. So it'd be negative force of gravity
Yes.
plus force of tension.
Yes. Equals mass times acceleration. Actually, M1.
Wait, okay, and then how does friction, not friction, normal force play into this? Like, how would normal force be in this equation?
So the normal doesn't enter because we are looking at the normal force and F para and F perpendicular, so the perpendicular weight are canceling out.
So
So
I don't have to write it out.
no, you have to, you would get extra points. You would say, along the perpendicular component, we have, or along the perpendicular axis, the two components cancel out. Now, you first determine the acceleration, then apply friction. If not, it doesn't work.
And if not what?
If you don't calculate where is the body moving first, you can't determine whether the friction acts on one side, the other side, or it doesn't act at all. Because it may just not move. The acceleration may be less than the static friction. At this point, if at the end of the day acceleration goes like this, then friction goes like this. But it may as well be that this damn mass here is heavier, even though it is tilted, than this one here.
Okay.
Okay. As easy as that. Now,
What?
as easy as that. Now, let's not get distracted by friction since we don't need any friction here, and let's get on with the second one, and then determining the acceleration of the whole system, please.
Okay, now the second one